In this segment, I want to talk a little bit about the atomic model. The atomic model is one of the most successful models in science. It describes everything around us based on these fundamental building blocks called atoms, right? And maybe you're not used to calling it the atomic model, right? Like, maybe you're just thinking about it as, oh, well, this pencil is made up of atoms. I know that. I'm made up of atoms. Maybe you just know that. Maybe you don't think of it as a model. But it is a model. And I think it's a great example of a model because have you ever seen an atom? And of course the answer is no. Has anybody ever seen an atom? Again, the answer is no with a few tiny caveats. Atoms are so much smaller than the wavelength of light that our eyeballs can see that we certainly can't just see an atom with a microscope, right? Because and this is something we'll talk about a little bit more next semester. You just cannot image something with a wave if the wavelength of that wave is larger than the object you're trying to image. Okay, so you just can't do it. So visible light certainly won't work. You can't even use an electron microscope because even an electron microscope, which can have much smaller wavelengths and therefore can image much smaller things, still an atom's way smaller than the wavelength produced in an electron microscope. Scanning tunneling microscopes can create some sort of image of where atoms are, but that's different from an image of an atom. I don't know, a couple years ago, there was an image floating around social media. It was supposedly a picture of a single atom. It wasn't really. What it really was it was capturing the light emitted by a single atom. That's different from an image of an atom, right? So at any rate, my point being that nobody's ever seen an atom. And it's just in a model, right? It's a thing that exists in our mind that helps us to adequately explain this world that we live in, right? Okay, so what is the atomic model? Well, the atomic model contains these pieces, which you've probably seen in another class. The nucleus is this part in the middle. It's an incredibly dense spot here. It's a dense little bit of matter, I suppose we could say. And it contains protons and neutrons. And of course, the protons are positively charged and the neutrons are neutral. Winging around the outside of that are negatively charged electrons, which we often describe as orbiting the nucleus, right? But again, no one's ever seen an electron orbiting the nucleus. And if this is the image in your brain, it's not a bad model. It's just a model. And it's maybe not the best model either. In fact, we should think of these electrons winging around the outside as being, they're not really like a planet orbiting the sun. Really, they're more like a electron wave. And so this is something we'll talk about again next semester a little bit. These electrons behave as much like waves as they do like little balls orbiting some central nucleus. And so, well, this may be the visualization we have in our brains. There's two real big problems with it. And the first is these electrons, they don't really just orbit like that, right? Really, they're forming what we might call a standing wave pattern. And so here's some visualizations of various standing wave patterns that the electrons can form. And those of you that have had some chemistry will recognize these as the orbitals, right? The SPDEF, etc. orbitals. So again, this atomic model is just a visualization in our brain, and we think it's really how the world works, but it's just a model. It adequately explains observed phenomena. Another problem with this little picture here is the nucleus. I mean, well, let's just look and see what's wrong with this. The perspective is real wrong. Right here, we're seeing the nucleus has taken up, most of the space of the atom. But we only make it like this because in order to draw something where you can see the nucleus and the electrons, it's got to be grossly out of proportion. And so, to kind of help us visualize the actual structure of an atom, well, let's visualize Mile High Stadium. So here's Mile High Stadium, and let's imagine that this is an atom. Okay, so where would the nucleus be? The nucleus is like a grain of sand on the 50-yard line, and the electrons are out in the stands somewhere. So this gives you a feeling for, it's just an analogy, but it gives you a feeling for the amount of space in an atom, right? The nucleus of an atom only takes up a few quadrillionths of the volume of an atom. And then there's these standing electron waves going around the outside. So what is an atom? It's almost completely empty space, which is really weird to think about, isn't it? Like this coffee cup, which seems so solid, right? It turns out it's mostly empty space. Only a few quadrillionths of the total volume of this coffee cup is actually taken up by stuff. Protons, neutrons, electrons. The rest of it is literally empty space. That includes me and you, and your ex-boyfriend is just as vacuous as you thought. So it's kind of crazy. It's kind of crazy to think about. Okay, but that's the atomic model. So when was all this discovered? Right around the turn of the century, between the 1800s and the 1900s. In 1897, J.J. Thomson announced the discovery of the electron. The proton followed in the early 1900s. The neutron wasn't discovered until the 1910s sometime. So, it was about a couple of decades there as people were figuring this out, able to probe smaller and smaller scales. So atoms are these impossibly small building blocks that make up everything around us. And what's crazy is there's not that many ingredients that you need in order to make, a computer, a calculator, a person, some coffee, right? The ingredients are very similar for all of those things. And there's only 118 different types of elements. And so here's the periodic table. You've certainly seen this before in another science class, I'm sure. But of this 118, not all of them are the ingredients of the stuff around us, right? A lot of those are actually man-made. There's only 92 naturally occurring elements. The heaviest of the naturally occurring elements is right here, uranium. So there's 92 naturally occurring different kinds of atoms. We call them the elements. And everything in the universe is made up of those same 92 ingredients. It's crazy to think about. And we're pretty sure that there's not more ingredients out there that no one's discovered, right? We're pretty sure that this is all of the elements that exist anywhere in the universe. Why? Well, they're ordered by the number of protons, right? So hydrogen has one proton. If you've got an element and it's got one proton, then it's hydrogen. Helium has two. Nowhere in the universe is there an atom that has two protons and isn't helium. If it's got two protons, it's helium, and if it's helium, it's got two protons. So the protons are what distinguish each element from another element, and there's no such thing as a half a proton, right? So in other words, an element with two protons is helium, an element with three protons is lithium, and there's no such thing as 2.5 protons, so there will never ever be an element that goes in between helium and lithium. So we don't think there's any unaccounted for holes in our periodic table. And like I said, the heaviest naturally occurring element is uranium right here. And as you get heavier, as you try and add more and more protons beyond 92, you end up creating unstable elements that are around only for a very brief amount of time. So any of these that have brackets around the atomic weight, well, those are all elements that have never existed for long enough to really, in any significant quantities, to determine what the average of a bunch of it is, because it's not a thing. There's not a bunch of it around to find the atomic weight of. So again, there's 92 different ingredients that makes up everything in the universe. Isn't that crazy? It's super weird, right? Okay, so let's look at some of the information that is on this periodic table. This number at the top is the atomic number. That is the number of protons. And like I said, the number of protons is what makes an element what it is. If there's an element and it has 6 protons, then it is carbon. And if you have carbon, then you have an element with 6 protons. This is the symbol. Symbol is always either 1 or 2 letters, and it always starts with a capital letter. If there is 2 letters in it, the second letter is always uncapitalized. This number down here, we call that the atomic weight. And for right now, we'll say that it is how much an atom of the element weighs in a unit called atomic mass units. So an average carbon atom has an atomic weight of 12.01 atomic mass units. And this has other interpretations, which we'll get to in one moment. The atomic number, that's this number here at the top. Again, that is the number of protons. And if the atom is neutral, then it's also the number of electrons, right? Remember, the atom is made up of positively charged protons in the nucleus and negatively charged electrons. If there's equal numbers of both, then we have a neutral atom. If those are unbalanced, we have something called an ion, which we're not going to go into a lot of depth into here today. The atomic mass number is the sum of neutrons plus the number of protons in an atom. So for any atom, this will be a whole number. Why? Because we can never have a half of a neutron or a half of a proton or a tenth of a proton or something like that. So we add up neutrons, we add up protons, and we get just a number. Now notice that's different from the atomic weight. This is sort of like the average atomic mass number of a whole bunch of carbon atoms. Any one individual carbon atom can only have an atomic mass number that is a whole number. So you can see that a typical carbon atom must have 6 protons. Well, they all have 6 protons, but it must also have 6 neutrons. Why? Because protons plus neutrons equals the atomic mass. That would be 12. Now, this can be interpreted as the average of a whole bunch of carbon. So there must be some carbon out there that has either 13 or 14 for an atomic mass number. Since all carbon has 6 protons, that means there must be some carbon out there that has 7 neutrons or 8 neutrons. And indeed there is. Those are different isotopes of carbon. So isotopes are same element but different numbers of neutrons. So any carbon will always have 6 protons. If it doesn't have 6 protons, then it isn't carbon. However, carbon can have either 6, 7, or 8 neutrons. Those are different isotopes of carbon. If we take the average of all the isotopes, then we get the atomic weight here. Okay. So the atomic mass can be interpreted as the atomic mass number times U, where U is 1.66 times 10 to the negative 27th kilograms. And so we can interpret this number in a couple of different ways. It is the atomic weight in atomic mass units. If I get a whole bunch of carbon together, then this number right here is the average atomic mass in atomic mass units. Now, one thing about atoms is that atoms are very small. It's hard for us in our little human brains. In fact, I think it's hard for us to wrap our little human brains around just exactly how impossibly small atoms are. Take a deep breath. There's as many atoms in a breathful of air as there are breathfuls of air in the atmosphere. There are as many atoms in an apple as there are apples that you could fit in the earth. There are as many atoms in a thimbleful of water as there are thimblefuls of water in all of the lakes and rivers and glaciers on Earth. It's wild, right? Atoms are so small. And so we've introduced this idea of, we call it Avogadro's number, and it's also called a mole, and it's just a very large number. So you may have encountered this in another class. 1 mole is 6.02 times 10 to the 23rd, and it's just a big number. I like to use the analogy that it's just like a dozen, except bigger, right? A dozen is 12. I could say I have 2 dozen eggs, or I could say I have 24 eggs. It doesn't matter. It's the same thing. Similarly, a mole is just a big number. It happens to be a huge number. It is 6.02 times 10 to the 23rd. That is a very large number. And we call it 1 mole. 1 mole. And it has some importance, right? And the significance of it goes back to this number right here, the atomic weight. If I have 1 mole of atoms, then I have the atomic weight in grams of that substance. For example, if I have a pile of carbon, and in that pile of carbon, I have 6.02 times 10 to the 23rd atoms, then I have 1 mole of carbon, and the mass of that 1 mole of carbon will be 12.01 grams. So, this is called the atomic weight. It's also called the molar mass. And so this equation right here relates the mass of your substance, the molar mass, and the number of moles. I almost think it's easier to visualize this if we bring the molar mass to the other side. So the number of moles times the molar mass gives us mass in grams. Makes sense, right? So if we had 2 moles of carbon, then we would have 24.02 grams of carbon. Okay. We can get between number of moles and number of particles. This is an equation. We've used something similar a lot, right? The total number divided by the number per package gives you the number of packages. In this case, the packages are moles that we're imagining in our mind. Okay, let's do a quick example. A gold bar at Fort Knox has a mass of 12.44 kilograms. How many moles of gold atoms does it contain? Okay, well, it contains, the molar mass of gold is 196.967 grams per mole, right? So we can read that right off of the periodic table. And we have a total mass of 12.44 kilograms. So what we should do then is we should do this. N is equal to the mass divided by the molar mass, right? And so in this case, my mass is, and let's go ahead and convert that to grams, 12,440 grams divided by 0.967 grams per mole. Okay, so I ran my calculator and I got 63 moles. All right, 63 moles. How many atoms is that? Well, we know that the number of moles times Avogadro's number gives us the number of atoms. And so we can take 63 moles times 6.02 times 10 to the 23rd. And now we can run our calculator on that, and we get 3.8 times 10 to the 25th, right? So a huge number, right? Just a huge number. So that's the power of mole, right? This idea of a mole, it helps us to wrap our brain around these really, really big